maximum efficiency, maximum draw length. That is just like a win in every single direction, if it were true. Hi, it's Todd from Todd's Workshop and Todd Cutler here, and I have recently made this Chinese crossbow trigger system. But it's not for any old crossbow, it's for a siege crossbow. But the Chinese had all sorts of things, and they had ordinary ones, and they had crazy ones, like this. And that's what I'm going to be making. But as you can see, this is not a fantasy thing. It was a real object. And they lasted sort of over a lifespan of about 800 years. So they must have been really good. But the real problem is there is simply not enough information for me to just go out and make one of these. This drawing is kind of the best I've got. And so I had some initial thoughts to it, very exciting. I've been developing those, and that's what this film is really about, explaining where my thinking is now. And then if you can give me any help with it to develop it on, that would be brilliant. And this project started with some simple models to help me understand what's going on, see the string movements and the bow movements and the draw lengths. But I was kind of pondering things. And you came up with fabulous comments. I've been reading them, digesting them, thinking about them, trying to work out what's going on and why I want to be doing it. So I warn you, this film is really about looking at the physics of the whole thing, or at least me trying to understand it. It's not yet about me building one. So let's start by going back to this drawing, which is my source material. Now, clearly it's short on detail. Clearly it's been stylized. I think we can all agree on that. And because it's been stylized, it means that we can't truly trust any of the detail in it. However, there are some things which I think are going to be quite clearly correct, which is that you have a rear-facing bow here and the two front-facing bows. I think we have to assume that that's right. But then we come to things like the distance between the bows. Can we trust that? Well, I don't think we can. I think that is just a stylization. So why have I jumped in and assumed that immediately? Well, have a look at this Eastern-style bow. It's a cheap fiberglass one, but it's a recurve, the same sort of format as those. Now, if I pull that back, look how far those limb tips are coming back. That is the way it operates efficiently. That is the way those bows are designed to operate. And what you then need is a bow on this side and a bow on that side with enough distance between them that the limb tips will clear each other, plus a little bit of distance to sort of ease your rigging. Now, you might say, well, what you could do is just overlap the movement of the bows, and then you'll compact up your machine, which is going to be a good thing. But the problem with doing that, of course, is that if you have a rope tied off on this limb tip and a pulley on that limb tip, once they start to curve in, if they get beyond that point, they can't exert any force on each other anymore. And that means that they could get to that point, which would not be in that drawing, maximum draw at all, and they can get no further. So there has to be a greater distance between those two bows that is shown in that stylized drawing. So at least in my head, I'm very clear that these two bows here need to be separated further apart. But then we come to the actual way that all of the string rigging is done. Now, we can agree on a few things. It's short on detail. It's not very clear. It's obviously quite complicated. And I'd also say it's quite clear that it involves some sort of sliding strings. I'm going to use the word pulley if you want. So, of course, what's really annoying for me working on this is that whatever detail is going on here where the strings pass is missing. And they've missed it for one of two reasons. Either it was there and they didn't put it in, or the detail was so simple there was no need to put it in, which would mean that the strings were passing over the bows. No pulley, no ring, no nothing. Nothing to show. So if there was nothing to see, or if they just didn't show the technology, what options were there? Well, if there was nothing to see, that means that the string is probably going through a groove over the ends of the bow or through a hole here. Now that might or might not give you string management issues, because we're used to seeing a bow just sort of come back and you don't think much about it. But have a look at this slow motion footage by Andreas Bickler on a composite crossbow, Western European. But if you don't know his work, it's extraordinary. Go check his channel out. It's fantastic. But you can see from the slow motion footage, the bow is twisting, rippling, moving about. That may well give you string management issues. Even if it doesn't, pulling the cord over wood, even if it's greased, is going to be higher friction than a pulley. And that is why we moved away from the old traditional pulley blocks where you did exactly that, where the rope just slid over a polished wooden surface, and moved towards wheels, because it works better. So I'm going to assume that the Chinese understood that things worked better than just pulling it through a wooden groove. So they might have done it through a little metal ring. And again, it's going to be lower friction than a wooden groove. But if it's a little metal ring and they haven't shown it, that's fine. But again, it's going to be quite harsh on the string. It's going to wear the string faster. It's going to wear the string faster than a pulley would. And they understood pulleys, they knew pulleys, they had them. So as far as I'm concerned, that's the way I'm going to look, because I think that's what they would have done. And now, a word from Todd Cutler. Our Black Friday sale has finished, but don't worry, we're rolling straight into our Christmas sale, as you can tell. But we loved our advert so much, we're showing it to you again. There's Fridays, and there's Todd Cutler Black Fridays. And our prices are on fire. We're slashing prices. We're smashing prices. Some of our prices are even cut in half. The Todd Cutler Black Friday sale. Do not miss it. And back to the film. So now I've decided roughly where I'm going to position the bows on the actual machine. I've decided that I'm going to use pulleys. I need to know how I'm going to rig the bows up. So when I started looking at this, and what I got really excited about was the opportunity to maximise the draw length. Now, I mess around with bows quite a lot, and I do understand that draw length has a vast impact on how fast and how powerful the arrow travels. So as an example, I make crossbows, Western European ones, but I make a Balestrino, tiny little bow, and it's got a draw length on it of about 45, 50 millimetres. But it has a 200-pound bow on it. But it delivers so little energy, it's almost laughable. It was a toy. But if I then translate that to a 200-pound full-size crossbow, suddenly you're getting something that is man-killing. Same power of bow, but the power stroke, the distance that it pushes the arrow over is very different, and the end result is very different. So that seemed to me like a really obvious thing to do, maximise the stroke. And you can do that by tying off the cord here at the top, passing it down, putting it through a pulley or a ring, coming up to another pulley or ring, and suddenly you're getting very, very long power strokes out of relatively small bows. Well, that is going to be exciting. And I got excited. However, and correct me if I'm wrong, because I think I'm on pretty shaky ground here, my physics is very old, but I think what's going on is that we have a 2-to-1 reduction on a pulley here, and a 2-to-1 reduction here. So 2 plus 2 is 4. What that means is that you will get out of this system 4 times the power stroke. That was what was getting me excited. That is, if you assume that there's a 50 centimetre power stroke on each of these bows, multiply that by 4, that is a 2 metre power stroke on your arrow. So I'm like dancing with joy. This is absolutely brilliant. But the flip side of that, of course, is there is a 4-to-1 reduction in the force. And so what that means is it's not going to be, let's say, thrusting with 100 pounds of thrust all the way through that 2 metre length. It's going to be doing it at 25. And that is not quite so exciting. But the other thing that was abundantly clear to me is that these bows would then need to be of different weights. And if there's one thing we know about the Chinese, they do like to try and standardise things as much as they can. And it would strike me as odd that this one would be a quarter weight of this one here. So my first thoughts are beginning to become a little less exciting. I have non-standard bows. I'm thrusting the arrow with a quarter of the force that it might otherwise do if I rig this differently, although the draw length is longer. But then we also have 4 pulleys in here. And although pulleys reduce friction, they do not eliminate it. And so now we have 4 pulleys, all of which are introducing friction into the system. So what I suddenly got excited about in that first film and thrilled about, I am now very much doubting. And I don't think my initial thoughts about it were on the right track at all. So what happens if we simplify the system? We remove some of the complexity out of it. Well, you can tie the bows together here and here. That means that you're losing 2 of the pulleys out of the system, just leaving these 2 here. That reduces the friction. But you have also reduced the draw length, but you've increased the power of the thrust on the bolt. So you're losing some things, you're gaining some things. But I think overall what you have is a far more plausible system. But now I also think you're beginning to be able to look at standardising the bow weights for having a bow weight of 1, 1 and 1 as opposed to quarters and halves. At first glance, it looks like this system should work really well. So these two bows here are tied together to create a bow weight, collectively, of 2. You have a bow weight of 1 here. That's obviously half of that. But you have a pulley reduction system here. And so the force that it's applying equalises over the 2. As you draw it back, first glance, they should all deflect about the same. Absolutely brilliant. Now that is an ideal situation because what it means is all the bows are going to deflect to the same amount. So you can keep on drawing that till they're all at maximum deflection, maximum efficiency, maximum draw length. That is just like a win in every single direction, if it were true. But look at this again. The front bows are flexing more than the rearward bow, even though they're all the same, even though in my understanding they should flex the same. And it's not just me that's having this problem. Have a look at this video by Stephen Gardner of his machine and look at the rear bow on it.
And you'll notice that the rear bow is actually relaxing as the front bows begin to come under tension. Once they're at full draw and they start to stack, the rear bow starts to draw. And it gets to about 80% before I run out of stroke.
So I'm trying to wonder what the heck is going on, and I can be honest with you and say that I am totally lost. Now the first reason that I'm beginning to get really lost is if this pulley system was tied off in a conventional pulley system way, then I'd understand things a bit better. But it's not. Because this tying point here is also on a bone limb tip, obviously, but that means that it's flexing too. And so the whole 2-to-1 ratio thing that I was trying to work this out on just is no longer true. So what I'm thinking, in fact, is that actually this probably isn't operating on a 2-to-1, it's probably operating on a 1-to-1. It's just increasing the draw length. That's all it's doing. But remember, these two bows collectively together are twice the weight of this one. So in my head now, I'm thinking that these two bows should flex half as much as the rear one. And that's not the case. But if that wasn't enough to muddy the waters, there's another aspect which does. So this central bow here is being drawn with vector angles on the string here. So basically like a conventional bow would be drawn. But the front bow and the rearward facing bow are going with the 0 vector angle on the string. They are being pulled directly. And that is not how bows are weighed. So what that means is that these two outer bows will inevitably be operating in a different way. They are operating in a different way to this central one. So they might all be 100-pound bows, but it doesn't mean that they would all exert 100 pounds into the system. Vector pull, bringing the limb tips in. Straight pull, pulling them straight down. They are different things. We're going to try a little experiment now to show the importance of vector angles and how that changes everything. So this bow here is, I don't know, 15, maybe 20 kilos in draw weight, something like that. I'm going to mount it in the vise, and I'm going to draw it using a crane scale, a measuring scale, from the centre of the bow here. Tomesh is going to come in, and he's just going to measure a distance, limb tip to limb tip, and I'm going to repeat the experiment again, but doing a straight draw where there is 0 vector angle. Tomesh, come on down. So, big crane scale. It's going to come into the middle. I'm just drawing that now. So we have got
88 on distance.
88 centimetres, and that's 13.5 kilos. So 13.5 kilo draw, and it's 88 centimetres tip to tip. Let's do that with 0 vector angle. So we're repeating the experiment now with a straight draw on it. So I'm just going to load it up. There we go, 13.5. And what's the distance?
113.
113. So previously, at 13.5 kilo draw, it was 88 centimetres. And this time it was 113.
113.
That is a huge difference. That shows the importance of vector angles. It shows the way bows are designed to work. So suddenly now, what we're going to be doing is using two bows, the forward and the reverse, in a totally different way. So the fact that all 3 bows are the same draw weight actually doesn't matter because they're not operating with the same draw weight. So that's all very interesting, I'm sure. But what does it actually mean to my triple bow Chinese siege engine crossbow thing, the Oxbow? Well, fundamentally, it means that however much I may want these bows to be exactly the same, I do not envisage that at all. I cannot see it. Because you have now, as far as I'm concerned, 2 different bow weights. These ones have to be different to that. And you have 3 different positions for all of these bow weights. And that's just assuming that the rigging is done correctly. So there's an awful lot of variables in here, none of which we know. And I haven't got years and years to work all this through. I haven't got generations of craftsmen to work it all through. So where does it leave me? Well, simply put, it leaves me out of my depth. I don't really know what's going on here because I seem to have conflicting information, conflicting logic. I don't have enough information from making it. There are too many variables. So this is, as far as I'm concerned, even if we can put it through some sort of engineering finite analysis type bit of software, there is so much research work for me to do because, you know, force distance curves are not constant on these bows, that I can't even just hand it over to an engineer and ask them to solve the problem for me. So I have got 2 choices. And the first one is go back to university, do a PhD and spend 3 years studying this thing. The second one is buy some bows and just make it work. And I think you all know me well enough to know which option I'm going to take, because that's not going to be a PhD. So if you have suggestions, if you have ideas, please throw them out there, because there is some really weird stuff going on here I don't get. But the other thing, of course, is clearly I'm going to need a little bit of a variety of bows to do this. So if you're a bow shop, if you're a bow manufacturer and you want to sponsor me doing this, bring it on. I am going to talk to you because I've got a few bows to buy and I have got a really exciting, really interesting project to do with them. But before we go, you may have noticed that I'm wearing an Arrows vs Armour 3 t-shirt. This is just a reminder to you that it is coming soon. So for those of you who are not familiar with the Arrows vs Armour series, go check them out and just, you know, bookmark the page, do whatever it is you need to do, but make sure you watch those films when they come out. It's not going to be long now. And then the other thing as well is just to say, if you like this kind of content, we have fantastic websites that you are going to be interested in. Everything we sell on them is going to be of interest to you. And then, of course, finally, I have got my second YouTube channel, Todd Cutler, and our Patreon page, which is enormously useful, especially if I can't find a bow sponsor. So anyway, bring it on. I hope you've enjoyed it. It's been a talky one, this, but there's been a lot to go through and a lot on my mind with this. Join me. Come and make it happen. Work it out for me. I don't know, just help, whatever. Anyway, I hope you've enjoyed it, and I'll see you again. Sorry, I've had to come back again to show you this. I was thinking last night, I rigged it up again this morning, and check this out. All the bows bend the same. So I've worked out how to balance the bows, and to make that work, I actually have a formula for it. Methodology. Still don't fully understand what's going on with pulleys and things, but anyway, what it does mean is that there's going to be a part 3 where I explain my methodology, and that gives me the information to go and buy the bows.